Since a very long time, humans have been trying to create materials with better and better properties, studying them and making useful products out of them as our demands grow. Electrical conductivity is one such property. It is the measure of the ability of a material to conduct electricity. Based on electrical conductivities, materials are broadly classified into conductors, semiconductors, and insulators. Have you ever wondered how the solar cells in the solar panel on your roof work? Or maybe you haven't seen a solar cell yet. In that case, have you thought how that LED light bulb on your wall glows? Or why our parents prefer LED bulbs over CFL bulbs? Well, to answer all this, we will have to look deeper and ask, what are they essentially made up of? And that's the topic of this video, semiconductors. Semiconductors have electrical conductivity ranging from around 10 raised to minus 6 to 10 raised to 4 Siemens per meter. This electrical conductivity lies in between those of conductors and insulators. Silicon with atomic number 14 and germanium with atomic number 32 are two trendy semiconductors. In semiconductors, the conduction band and the valence band are separated by a band gap having forbidden energy gap less than 3 electron volt. This is around 1 electron volt for silicon. Due to this small band gap, even at room temperature, the electron in the valence band has enough energy to cross the band gap and jump into the conduction band. This conduction mechanism can be easily explained using band theory of solids. Semiconductors can be either intrinsic or extrinsic. Pure semiconductors are called as intrinsic semiconductors. They do not have any impurity but may have defects like pure silicon and pure germanium. Consider silicon. It is an element in the third period and the 14th group of the periodic table. With atomic number 14, it has the electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p2 with 4 electrons in the outermost shell. Consider a two-dimensional structure of pure silicon material. To obtain octet, each silicon atom is covalently bonded by 4 neighboring silicon atoms. Since all electrons are bonded, there are no free electrons at absolute zero. Thus the conduction band is empty and our silicon now behaves as an insulator. As the temperature increases, some electrons may gain enough energy to break the covalent bonds, becoming free electrons and leaving a vacancy behind. These thermally generated electrons move into the conduction band and are called as conduction electrons. They are responsible for the conduction current, IE. The vacancy left behind in the valence band is positively charged and called as hole. Thus the number of free electrons created will be equal to the number of holes created. This is called as intrinsic carrier concentration, as they are responsible for electrical conduction in these intrinsic semiconductors. The motion of holes can be understood as follows. Consider a hole being formed at site A. Since this hole is positively charged, a neighboring electron, let's say from site B, may jump into this vacancy. This jump results in an electron at site A and a hole at site B. Now an electron from neighboring site C may jump to fill the vacancy at site B. This results in an electron at B and a hole at C. This process goes on and can be considered as the motion of holes. This hole motion is responsible for hole current IH. Now consider the action of an external electric field. The free electrons move towards the positive potential and the holes towards the negative potential. Thus the total current is the sum of conduction current IE and the hole current IH in the direction of external electric field. This was how the generation of conduction electrons and holes occur. Consequently, recombination of conduction electrons and holes may also take place when the electron in the conduction band falls into a hole in the valence band. We are not done yet. As we have seen, both electrons and holes take part in electrical conductivity in semiconductors. Thus, the total electrical conductivity in intrinsic semiconductors is the sum of conductivities due to both free electrons and holes. This total conductivity depends on the temperature. The conductivity is very low at low temperatures, but as the temperature increases, the concentration of free electrons and holes increases Thereby the conductivity increases. Purity of the semiconductor. Semiconductors with high purity can now be made, and imperfections in the lattice. But it is always advantageous to have something better and more efficient. So one way we can enhance this conductivity is to have large concentration of conduction electrons and holes. This can be achieved by adding controlled amount of impurities called dopants. This addition of impurities results in the formation of one or more energy levels in the band structure of pure semiconductor. It significantly affects the properties of the semiconductor. This method of adding impurities is called as doping, and the obtained impure semiconductor is called as extrinsic semiconductor. One condition is that the size of the dopant should be comparable to the size of the semiconductor atom so as to not distort the original pure semiconductor lattice. Now, since silicon and germanium belong to group 14 of the periodic table, the impurities commonly added belong to group 15 called as pentavalent impurities like phosphorus, arsenic, antimony, etc. and group 13 called as trivalent impurities like boron, gallium, indium, etc. So depending on the type of impurity, whether pentavalent or trivalent, we get N-type or P-type semiconductor respectively. Let's see what happens when we add pentavalent impurity. When small quantity of pentavalent impurity, let's say phosphorus, is added to pure semiconductor during crystal formation, some of the phosphorus atoms will get locked into the silicon crystal lattice. The phosphorus atom will use 4 of its valence electrons to form covalent bonds with 4 neighboring silicon atoms, while the 5th electron is weakly bound to it. This loosely bonded 5th electron occupies a state just below the conduction band. So at 0 Kelvin, the phosphorus atom is unionized and the conduction band is empty. The ionization energy of phosphorus, which is the amount of energy required to set this 5th electron free, is much smaller than the band gap energy. Thus, as the temperature increases, the phosphorus atom will donate its 5th electron to the conduction band first without producing a hole. These types of impurities are called donor impurities, and the level formed is called as donor level. Then at higher temperatures, the bonds in the valence band will be broken and further conduction will take place. So the conduction electrons here are due to both that produced by dopant as well as that produced thermally in the intrinsic part, while the holes are only produced thermally in the intrinsic part. As a result, in doping with pentavalent impurities, there are more number of conduction electrons than holes. This type of semiconductor with electrons as the majority charge carriers and holes as the minority charge carriers is called as N-type semiconductor, where N negative electron, you get the idea, right? Anyways, moving forward, let Ni and Pi represent the electron and hole concentration in intrinsic semiconductor, and N and P represent the electron and hole concentrations in N-type semiconductor. Then we can clearly notice that N is greater than Ni and P is less than Pi. Remember, N-type semiconductor is electrically neutral. Why, you ask? It's because for every electron donated by a donor atom, there is an equal and opposite charge left behind at the donor. Now, what if we added trivalent impurity? Well, you guessed it right. Maybe we will get a P-type semiconductor with more number of holes than the number of conduction electrons. The impurity will be called as acceptor impurity, and the level created just above the valence band is the acceptor level. But this video is already pretty long, so my fellow brave warriors, I leave this mission on to you. Study about the P-type semiconductor. Or maybe I'll make a video on it later. Anyways, bye bye. Peace be upon you.